Hello everyone, my name is Nilofar. I'm ASR number 3. I'm originally from Iran and I'm currently doing my PhD at KTH University. My project is about identification of non-linearity in aeroacoustic systems. And when I say the system, I mean perforated plate. The reason behind choosing perforated plate is that they are a really good sound absorbing tool and they are efficient and they can resist in a harsh environment. Let's take a moment and see how we see the nonlinearity in the perforated plate. In order to understand the nonlinear mechanism, first we need to step back and see what happened in a linear regime. Imagine this yellow part or perforated plate, which are rigid. A gap between them is perforation. And in upstream, we have sound source, which produce a sound wave, which is a standing wave. At some point, this sound wave meet the perforated plate, and then we have an acoustic particle velocity amplitude through the hole. But remember, we are in a linear regime, so all this energy will transfer to viscous losses. Now we are increasing the sound level. We would like to go to the nonlinear regime. And if we increase high enough, then we have a vortex shedding at the outlet of orifice, which is nonlinear. And this nonlinearity are associated with the high particle velocity amplitude through the hole. And this nonlinearity basically make an interaction between the harmonic. So what we are going to do, we would like to extract this nonlinear property from limited set of experiments. Let me show you with an example what I mean about interaction between harmonics. In x-axis, I have frequency. In y-axis, I have autospectrum, and this is one of my measurements for high excitation level. If we were in a linear regime, we only had autospectrum at the excitation frequency. But now you can see it in other frequency as well. And if you look closely, you can see the odd harmonics are dominate nonlinear phenomena. And the greatest one is third of the excitation frequency. Before seeing the actual setup, let's see the schematic of that. I have a loudspeaker as a source which generate the signal. I have microphone both in upstream and downstream, and in total there are 6. They help me to capture pressure and velocity at the sample, and my sample is in middle of the duct. And the ending condition of this duct could be rigid, open, or it can have absorption material. The model which studies the nonlinearity in this case is a scattering matrix. You can see that we have a pressure incident and pressure reflection. And the red frequency is high frequency and the blue frequency is low frequency. If we were in the linear regime, the only parameter which could relate P incident to P reflection was reflection coefficient. But now we are in nonlinear. And the main nonlinearity I show you also is interaction of the harmonic between low frequency and high frequency. This is my actual setup and these are my sample. I put the sample in the middle of the duct, and with 3 ending conditions, I capture pressure and velocity at the sample. And then with the help of model, my scattering matrix, I study reflection factor, transmission coefficient, and absorption of the sample. To what I said, there is more to know and there is more to explore. And we hope we can come up with a good solution for that. Thank you for your attention.